So this section is going to be on geometry. There's a lot of algebra in it, just because the relationships between things in real life and geometry, there are relationships that show up algebraically. So for instance, here's a very easy one. We have things that are called perfect squares. A perfect square is the product of two whole numbers. So for instance, 2 times 2 is 4. 4 is a perfect square. 3 times 3, 9 is a perfect square. 4 times 4, 16 is a perfect square. Why are they called perfect squares? Because in geometry, if I was to draw them out, if I was to draw out the area of this, the first one would be what? 2 by 2, and would have an area of 4 units squared. If I had something that was 3 by 3, notice there would be 9 square units. That's why they're called perfect squares. You can actually show them visually as a perfect square. When I do a square root of a perfect square, then basically we're asking what number, I'll write it out, times itself makes. Okay, so when I have the square root of 64, we're saying what number times itself makes 64? Well, we already did 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, we're getting closer, 7 times 7, 8 times 8. There is a button in your calculator to do this, but you should be able to also know that 8 times 8 is 64. The square root of 81, what number times itself makes 81? How would I check that? Well, 9 times 9 should equal 81. The square root of 256. Well, now we're getting a lot bigger. I know 15 squared is 225. So, I know that 15 times 15 would be too high. So how about 16 times 16? Or, I'm sorry, 15 times 15 would be too low. Yeah. Or we could do the square root of 256, and it would tell us 16. What is the square root of 1? What times itself makes 1? Well, that would be 1. What's the square root of a fraction? It's really not that crazy. What times itself makes 1/4? Well, the way we multiply fractions is straight across. So really, we just end up with the square root of top over the square root of the bottom. We end up saying, what times itself on the top makes 1 over what times itself on the bottom makes 4. And we could check that. 1/2 times 1/2 is 1/4. So we can have square root of rational perfect squares, meaning it still has a whole, it has a rational perfect square. The square root of 9 over 25, we split it apart. The square root of 9 over the square root of 25. The square root of 9, what times itself makes 9? What times itself makes 25? So that would be the square root of 9 over 25. The square root of 50 over 128. If I split it apart, we have a problem, because there is no whole number that times itself makes the square root of. There is no whole number that times itself makes 50. But the good news is we're not ready to deal with the complicated stuff yet. This just can be simplified. Okay? So basically, 50 and 128 are both divisible by 2. So really, this is the square root of 25 over 64. Now we split that apart. What is the square root of 25 over the square root of 64? 5 over 8. The next thing we're going to deal with is what's called the Pythagorean theorem. Basically, for any right triangle, a right triangle has a 90-degree angle. For any right triangle, the sum of the legs squared, the legs are the two smaller sides adjacent to the 90-degree angle. The a squared plus b squared, the sum of the legs squared, is equal to the hypotenuse squared. The hypotenuse is the largest side. Okay, the hypotenuse is the largest side opposite the 90-degree angle. So what does this do for us? Well, I can basically solve for a third side of a triangle that's missing. So 5, 12, and x. I can now solve this by saying, well, a squared plus b squared equals c squared. What are the legs this time? Well, adjacent to the 90. So 5 squared plus 12 squared equals x squared. C is the hypotenuse there. 5 squared, 5 times 5, plus 12 squared, 12 times 12. That adds to 169. How do I solve this? Well, what number times itself makes 169? To solve this, to undo squaring, remember this is still inverse operations, to undo a second exponent, we do a square root. The square root of x squared is just x. The square root of 169, what times itself makes 169? Should be 13. On the next example, the legs squared, the a squared plus b squared, is not the 15 and the 25. It's the x and the 15. The smaller ones adjacent to the 90 degrees. So they're going to move this. Don't freak out about it. This just becomes x squared plus 15 squared is equal to 25 squared. X squared plus 15 times 15 is equal to 25 times 25. How would I solve for x? This is basically inverse operations. PEMDAS backwards, we start by undoing the addition using subtraction. And then we undo the exponent. We undo squaring by square rooting. The square root of 400, about 20. The length of the shadow of a building is 12 meters. The distance from the top of the building to the tip of the shadow is 20 meters. Find the height of the building. Okay, so here I have some building. And the shadow of the building is 12 feet. The distance from the top of the building to the shadow, so let's say we had a string here tied, is 20 meters. Sorry, these aren't feet, these are meters. Could you solve for the height of the building? We have a right angle along this relationship. We have a right triangle where a squared plus b squared, or height squared plus 12 squared, is equal to 20 squared. Height squared plus 12 times 12 is equal to 20 times 20. How do I solve for the height? PEMDAS backwards, right? Going backwards, any adding, subtracting. We undo the adding by subtracting. What would that be? 256. And to undo the exponent, we square root both sides. What is the square root of 256? I think we just did that. 16. So the height is 16 meters. We can also, and this occurs with the Pythagorean theorem, we can also get numbers that are not exact values, like the square root of 8. The square root of 8 itself is an exact value, but there is no whole number that times itself makes 8. Somebody's like, well, yeah, 4 times 2. That's not what square root is asking. What square root is asking is what number times itself makes. You should not necessarily know the exact answer, but you should know what this is in between. Because I'm going to use my calculator to get an approximation, but I'm going to make an argument that the square root of 8 is somewhere between the square root of 4 and the square root of, what's the next perfect square? So somewhere between 2 and 3 should be the square root of 8. Well, why? Because somewhere between the square root of 4 and square root of 9 is the square root of 8. In fact, probably closer to the 3, but a little less, so I'm guessing 2 point something. So the square root of 8 should be between 2 and 3. Now we check exactly what that is, the square root of 8. Oops. 2.828. Probably rounding that to the 100th. So how about 2.83? Square root of 30. I don't know what that is off the top of my head, but right below 30, 29, 28, 27, 26, 25, there is a perfect square. The next one would be, and I could count up from 30 if I want to, 30, 31, 32, 33, or I can just say, well, what's 6 squared? I'm going to argue that the square root of 30 is between 5 and 6, without even touching my calculator. I know that it's somewhere between 5 and 6. There's a number times itself that makes 30. What is that number? Well, let's see. Square root of 30. And we are going to approximate this. 5.477. Or rounded 5.48. And the minute we round it, it's not exact. But the idea is that we have a number that makes a little more sense. We say, you know what, I think approximately 5.48 squared is about 30. Dang if we're not right there, right? I could take it further and go, I think approximately 5.477 is about 30. It is about 30, right? I could take the answer that's in the calculator and square it, and it'll tell me it's dang close to 30. Now this still is not the exact answer. The calculator just keeps track of more decimals than we need to. But there is a number that times itself as 30. It just ain't pretty, but it is a real number. The square root of 110. What's the nice root below that? How about the square root of 100? After that would be the square root of, so I'm going to say probably closer to the 10, but that this is between 10 and 11. The square root of 110. $10.4881. So approximately 10.49. We're also going to be dealing with similar polygons. Similar means that they're not the same. It just means that the sides are proportional. So if triangle ABC is similar to DEF, then I can set up a ratio of the sides. This is similar to our last section on the percentages and ratios. I can basically say AB, this right here, is similar to DE. Then I can set up a ratio and say AB over DE is equal to BC is similar to EF. BC over EF. And last, AC is similar to DF. So I could set up a ratio, AC over DF. If they are similar, then the sides are proportional. We can set up ratios of the sides, and the ratios should stay the same, should stay proportional. How do we use this? Well, ABCD is similar to EFGH. Find the missing sides. Start setting up our ratios. If it is similar, then the sides are proportional. So AB over what? EF, which we don't know. AB over EF is equal to, pick another side, AD over 3 is equal to, let's do a third side, CD, or 2 over GH, is equal to, our last one, 4 over 2. This is a big deal, because all of the ratios should now be equal to 4 over 2. So what I can do is I can take each of these and set them equal to that 4 over 2. I can take 3 over EF is equal to 4 over 2, and I can solve this. We can cross multiply it if you'd like. Multiply both sides by 2 and by EF, by 2 and EF, and I'm left with 6 is equal to, what is that, 4 times EF? I can solve for EF by dividing by 4, and I'll go ahead and do it as a decimal. EF would be 1.5. I can take that same ratio, 4 over 2, and I can set it equal to AD over 3. This one, I'm not going to make too complicated. I'm just going to solve for AD. I'm just going to multiply both sides by the 3. So that AD is equal to 3 times 4, 12. 12 divided by 2, 6. And I can take that same 4 over 2, which I know is 2. You can deal with that if you'd like to. And set that equal to, what are we missing? GH. So how about 2 over GH? I want to clear these fractions, so I'm going to multiply everything by both the 2 and the GH. Both the 2 and the GH. So I'm left with 4 GH is equal to 2 times 2 is 4. Dividing by 4, GH is equal to 1. So basically, then one other way of thinking about it is by saying it's 4 to 2, then going from polygon ABCD to EFGH, we basically divide by 2. So that if I know that this is 3, that ratio should stay the same, and this one would be what? 1.5. If this one is 2, going here would be 1. But this, I have to figure out, I have to be able to go backwards, right? So I have to go, okay, well, if going this way, the ratio is divided by 2, going backwards, this one is 2 times bigger. So 2 to 4, 1 to 2, 1.5 to 3, 3 to 6. So you can do it visually, that doesn't bother me, but I want you to see that we could set up ratios, and that is a skill that we should have. Next thing I'd like to talk about is going to be angles. Specifically, we have 2 definitions we need to know. One is called complementary, one is called supplementary. Complementary actually has the root word, not to say something nice, that's complement with an I. This is complement with an E. Has a root word to complete. So literally, this is a complete or a right angle. This is where I have two angles that complete each other. What does that mean? They add to a complete or right or 90-degree angle. The visual for this, we've seen right angles already. It's that square, right? So if I take that angle at square and I cut it, then I will have angle 1 and angle 2, and those two angles add to 90 degrees. If they're supplementary, supplement is more than just completing. That's actually above and beyond. I'm missing the L. I don't know why I keep doing that. Supplementary is more than I need, above and beyond. A supplement to a book is where I have like an addition to the book. I have like extra resources. That's called a supplement. Well, a supplementary angle is where they don't add to 90 degrees. This is where two angles add to 180 degrees. Specifically, 180 degrees is a straight line. So if I take that 180 degrees and I cut it, angle 1 and angle 2 add to what? 180 degrees. A couple of examples of this. If one angle is 54 degrees, what is its complement? Well, they should add to 90. You could just say 54 plus what is 90? I'm going to write it out algebraically. The first angle is 54 degrees, plus the second one we don't know, should add to 90. Could you solve for that angle? Well, yeah, to undo the adding, we would. And get that x is 36 degrees. These two angles complete each other. They add to 90 degrees. If I have an angle that is 112 degrees, what is its supplement? Supplement means the angles will add to 180. So you could just ask the question, 112 plus what is 180? I'm going to write that out algebraically. 112 plus what is 180 degrees? We undo the adding by subtracting and get that angle would need to be about 78 degrees. Now we're going to be looking at some shapes and some other relationships. More specifically, when I have a polygon and we need its perimeter, the perimeter is basically the distance outside of an object. So the way that we get that distance is we basically add all the sides. Or we could say it's the sum of the sides. So here I have a square painting that is 260 centimeters. How long is each side? I have no idea. But I know I'm dealing with a square, which is very special, because that tells me that all four sides are the same. Whatever this side is the same, this side is the same, all four are the same. The perimeter means if I took all of those sides and I added them up, they should equal 216. Well, add up all four sides. What is S plus S plus S plus S? How about combining like terms? 4 S's. And that should equal the perimeter of 216. Because you now solve for the side length. To undo the multiplying, we divide and get that S is equal to about 54 centimeters. Find the perimeter of the following rectangle. So the perimeter here is going to be the sum of all the sides. Well, I have 1 3/8 plus 7/12 plus another 1 3/8 plus another 7/12. 1 3/8, 1 3/8. This is going to help me if I just turn these all into a mixed number. So multiply and add. So how about 11/8 plus 7/12? 11/8 plus 7/12. 11/8 plus 7/12 plus 11/8 plus 7/12. Now I could go in and give these a common denominator of 24 and then add them up, or I can let the calculator do some heavy lifting, about 47/12. The problem is I still need to be able to turn that into a mixed number, it said. So I need to be able to divide the 47 into, or the 12 into the 47. So let's see. It's going to go in 3 times with a mess after it. So what I can do is do 47 divided by 12. Goes in 3 times. That's 36, leaving us with 11 parts. So really our perimeter should be 3 and 11/12 yards. Find the perimeter of this figure below. Notice that one side length is not given. We have to figure it out. All these are right angles, which means we should be able to figure out the missing side. There is 1, 2, 3, 4, 5, 6 sides, but this one is missing. How do we figure that out? Well, this total distance here is 15. This is 7. So how much would be left if it were a complete shape? Well, 7 plus what would be 15? This needs to be 8. And if this is 8, so is this piece right here. 7 plus 8 would give me a total height of 15. Notice we can do it horizontally too, even though it is given to us. The 4 and the 6 should add up to 10. So now our perimeter will be the sum of these sides. So how about 15 plus 10 plus 7 plus 6 plus the 8 we figured out, plus the 4. I always like to stop and check. We said there were 1, 2, 3, 4, 5, 6 sides. I should have 6 numbers here. Good. So adding that up, 15, 25, 32, 38, 46. I'm thinking 50 centimeters. Double check that. Okay. The perimeter of a rectangular garden is 326 feet. The length is 91 feet. What is its width? No picture? Draw a picture. The length is 91 feet. The width is unknown. The perimeter is 326. So if we added up all the sides, well, what is the perimeter of a rectangle? A rectangle is sum up the sides. So it's the length plus the length plus the width plus the width. Adding that together, 91 and 91 is 182. Adding W plus W is 2W. And that should equal the perimeter of 326. How do we solve this? PEMDAS backwards. I'm looking for any adding and subtracting. That 182 is adding. We undo that by subtracting. So now that 2W is equal to, what would that be, 144? And last, we undo the multiplying by, don't put minus 2, that's ridiculous. We don't undo multiplying by subtracting. We undo multiplying by dividing so that we get the W is 72. So the width is 72 feet.